Gravity is not actually a force pulling you down. According to Einstein, you are constantly traveling along the straightest possible path through a four-dimensional landscape of space and time that has been warped by everything around you that has mass and energy. For more than 2 centuries before Einstein, Isaac Newton's picture of gravity reigned supreme. In Newton's universe, space and time are like a perfectly flat, motionless stage. Objects like planets, apples, and comets move around on this stage. And gravity is an invisible force acting at a distance, pulling any two masses toward each other with a strength that depends on their masses and the square of the distance between them. This law explained the motion of planets with astonishing precision. It predicted eclipses, tides, even the return of Halley's Comet. But it had 2 deep problems. First, it assumed gravity acts instantaneously across any distance, violating the cosmic speed limit set by light. Second, it treated space and time as rigid, unchanging backdrops, not as physical things that could respond to matter. Einstein's special relativity, introduced in 1905, had already shown that time is not absolute. 2 observers moving relative to each other will disagree on how long an event lasts, or whether 2 things happened at the same time. They will also measure different lengths for the same object, depending on their motion. What remains invariant, the same for everyone, is the space-time interval, a kind of combined measure of distance in space and duration in time. This hinted that space and time are not separate entities, but different aspects of a single 4-dimensional structure, space-time. If that was true, then any theory of gravity that kept absolute rigid space and time could not be the final story. Einstein's key insight came from a deceptively simple thought experiment. Imagine you are in a sealed elevator, far from any stars or planets, floating in empty space. You feel weightless. Now imagine the elevator is pulled upward with a constant acceleration of 9.8 meters per second squared, the same as Earth's surface gravity. Suddenly you feel your feet pressed to the floor. A dropped ball falls to the ground. Yet there's no planet, just acceleration. Einstein realized that locally, the effects of a gravitational field are indistinguishable from those of acceleration. This is the equivalence principle. It says, being in a gravitational field is, in a very real sense, the same as being in an accelerating reference frame. From this principle, Einstein made a radical leap. Instead of thinking of gravity as a force, think of mass and energy as telling space-time how to curve, and curved space-time as telling matter how to move. In mathematical form, this becomes the Einstein field equations, 10 interlinked equations relating the curvature of space-time, described by an object called the Einstein tensor, to the distribution of mass, momentum, and energy, captured by the stress-energy tensor. A planet orbiting the Sun is not being tugged by an invisible force. It is following a geodesic, the straightest possible path through the curved geometry created by the Sun's mass. Light itself, though massless, also follows these geodesics, so its trajectory bends when it passes near a massive object, producing effects like gravitational lensing. This new picture of gravity passes crucial experimental tests. It explains why Mercury's orbit precesses, its point of closest approach to the Sun drifts, by an extra 43 arcseconds per century beyond what Newton's gravity can handle, a tiny angle but one perfectly matched by Einstein's equations. It predicts that clocks run slower, deeper in a gravitational field, a phenomenon called gravitational time dilation, which we now routinely measure with atomic clocks on satellites and on Earth. Time quite literally flows at different rates, depending on how space-time is warped. But if mass and energy can curve space-time a little, there is a natural question. What happens when enough mass is packed into a small enough region that the curvature becomes extreme, so extreme that even light cannot escape? The answer hides inside Einstein's own equations, waiting to reveal the darkest objects in the universe.